So, hello everyone. Welcome to this last module, or second last, or for your advanced degree in computer science. So, I'm Giacomo Bergani, and so just a few things. So we're going to start discussing the coursework tomorrow, on which you're going to have like better details. But if you want, basically, you have all the code base now uploaded on Canvas. And for sure, if you're already accustomed with using Git, you could also have access to GitHub. If you're double checking for my personal GitHub account, then you actually have the code base. We're going to discuss that in more detail later on. But you would see that most of the classes that we're going to discuss in class are going to be discussed and implemented in the code base which is provided, so you don't have to type in your PC and redo everything that you're seeing on the slide. So you just click a button and then you run it. And you also have the specifications of the coursework, so if you want to start to have a look at that, you're more than welcome. But then I might suggest to you that if you're waiting for the entire module that allegedly we're going to finish by the beginning of next week, on Monday or so, then after Monday you'd have all the knowledge regarding to the module itself, and then after that we're just going to train for the exam and coursework, and we're going to do exercises together. So that's what we're going to do. But anyway, then you have all the specifications as a PDF on Canvas, as well as the code base regarding everything in it. But so actually, that is just me, where my office resides, in the third floor of the building, and my personal email. That is just me briefly speaking what I'm doing as a research, but you already picked your what is called your dissertation, so that is quite pointless and useless. Actually, the thing that is actually of more interest for you is actually what are the objectives of the module. So we are trying to understand the concept of concurrent programming. So there are actually a lot of ways on how that could be deployed and discussed, even from a theoretical perspective, but given this kind of conversion module, we're trying to do that as practically as possible. So we're trying to do that with having hands-on with the problems associated with concurrency by having also a programming part. And that is actually what the coursework will reflect. So you have like a realistic problem on which we're trying to apply concurrency, and we're trying to avoid some of the well-known problems. Appreciate, so how are we going to solve the problems? By exploiting explicitly constructs. But for sure they were defined theoretically, but now they are implemented in most of the available languages out there. And in order to do so, then we're going to see also how that is done in Java. So, or if the construct is not available in Java, how can I implement that, or how could I reuse the already existing API? So that is actually, roughly speaking, what the module is going to be about. Then definitely, as for the other module leaders, we're going to use IntelliJ IDEA. So if you haven't already done so, please download that, because we have like the community education for students, for which actually you could have free access to the software itself. And please double check whether the computer lab, when we're going to use that, is going to have like an outdated version of IntelliJ. Why? Because I'm trying to use with you as much as possible the newer version of Java. So I'm not discussing Java 21, but still Java 18, 19, something along those lines, like using the lambdas and all this kind of stuff. So if you're using an outdated version, you might have also SDK or JDK, which might be outdated. So, and everything comes with IntelliJ. So you don't have to install the software by yourself, because IntelliJ is also available as a zip. So you can also directly download the zip file and unpack it inside your computer lab, so to have like the most up-to-date version of IntelliJ, because I don't know whether they have updated that to the most recent version. And that is just the link to the repo that I was discussing before. So you're just clicking the link or copying and pasting that. then it's going to redirect to the code base. Nevertheless, for the lazier ones, so to speak, you also have the entire code base zipped on Canvas. So you have what is called? You're going to have like the marking scheme associated with the coursework and the code base itself, which should be extended, not completely drastically changed. So you're more than welcome than just exchanging and changing the code that is actually there. And then we're going to discuss that the day after tomorrow, basically. This is just briefly a recap of the kind of assessments that are going to be there. So the written part of the exam is going to be held the 29th of May. So you should have plenty of time for revising the module. And you have 90 minutes. And as feedback to that, then you have that all the exercises that are provided in Canvas are actually mimicking one by one the type of exercises that you're going to find on the exam. So otherwise, it would make no sense if I make you train on something which is completely different from what you're going to experience from the exam. So that is what you're going to have, one-to-one. So not exactly the same exercises, one-to-one, but the same kind of exercises, that's for sure. Then you're going to have that, and they should be already available. If something is not available, let me know. Also, the exam is going to be paperless, and that is going to be like a tryout. So please remember, as already sent as an email, to double check before the exam if all the credentials are actually working properly. Otherwise, you're going to have like problems because we're trying to reduce the amount of papers, and that should help. In addition to that, if something goes wrong with the PC, you should be allowed to bring the material associated to the module, and you have like a list of, so you have like the reading list, which is actually mapped by this kind of papers without necessarily a mastery down below, but the rest on the top is going to be one-to-one, what you could also bring to the exam. So you have like, if you need to have a book, because actually you have better access to the book rather than accessing the PDF on Inspera, then you have that. And you might be allowed, but I'm not sure, to bring the slides, but they should be still uploaded on Inspera. So as a backup measure, you could try to provide that to the classroom. And the visit will going to take place in August. So if anything goes wrong, there's also the time either you're not able to take the exam or you are failing the exam, there should be like a second chance in August. And the coursework, the deadline is going to be the 10th of May, so it's going to be sooner. So that's why we're trying to finish the module as soon as possible, so you have more like 2 weeks of time for completely dedicating yourself and doing the coursework. And then I might be aware that you also have other coursework to do, so that should mitigate somehow the effect. And that is just like the comprehensive list of references. So after this, then you could definitely start asking what is concurrent programming. So in order to understand what that is, let's do like some kind of etymology of a word of what is concurrency. So another thing that I'm trying to do is to make somehow interactive, but at this stage I'm just introducing something. So it's going to be just blabbering about, but I'm going to ask a lot of time to have questions or try to ask you if you know something. Please be aware. So concurrent programming is just what is something to be concurrent. So it means that something happens or allowed to happen at the same time with others. So what does that mean? Is for you required to have necessarily like a multi-threaded PC to actually have concurrency or not? Can we achieve concurrency despite having like a non-multi-threaded processor? Why or why not? It's partially written on the slides, that's for sure. But anyway, so you're younger than me, but if you have ever experienced like Windows 98 or something of the like, you still have the ability of having multiple programs running. but still at that time you didn't have like multi-threaded computers. So how would that happen? So you had something which was called multi-programming or physical concurrency. So you were sharing the same resource, which was the processor, but given the interleaving between one process and the other was so fast, you had the perception of multiple programs running contemporarily. Then you should have like a blue screen of death. Most of the time something went wrong, but nevertheless you had like the experience of having multiple programs running under the hood. So that's why, even though you don't have like a parallel PC or like multi-threading, still you could achieve like the same kind of parallelism by simulating something happening contemporarily by just interleaving the execution of the program. So I know that you didn't have like an operative system module, but that is usually mimicked by scheduling the order. We're going to see that also in Java, how does the library underneath implements that. But it's going to associate like a running time to the program. After that, it is going to be paused, and then you're going to schedule another pieces of program that is running up until one of the others is going to finish completely. So that is what is called interleaving. So you are making one process run against the other. And then you have logical concurrency or multiprocessing, on which you actually have multiple processors on which you could have actually access contemporarily to the same data. And that is actually when the troubles will happen, but the same kind of problems are going to happen nevertheless even in multi-programming. So it's not because you have actually real concurrency that you're going to have problems. But another question is, what kind of problems might arise from concurrency? But then we're going to clarify that in this lecture. So that's why usually you might think that might be completely different kind of problems, but really they exhibit the same kind of behavior, because the thing that matters is actually what you perceive from your own side. And actually you would see the perception of multiple programs running contemporarily. So the problem is that you might see at the end of these slides that there might be that in one way you're experiencing problems and in the other way you're not having problems. So the way is, how could I force the execution of the program in the way that I'm avoiding these problems? And so that is what concurrency programming problems are trying to solve. So trying to avoid the problems and have like a scheduling order or like order of execution that avoids this kind of problems in concurrent programming. Then that is also a clarifying slide, because some other students in the past were saying, okay, but I'm interested in applying that to, for example, high performance computing, and applying that to distributed computations and distributed algorithms. What about that? So the problem is that this is actually going to be like a conversion module at the end of the semester, for which also discussing data parallelism or operation parallelism in more detail is going to take more time. You need to discuss advanced algorithms, have like a better discussion on how to avoid some of the problems, but still that might be possible. So the idea is, after you graduate, if you want to investigate more on how to do like distributed algorithms or concurrent algorithms, then this module will give you nevertheless the idea on how you could implement in practice this kind of stuff. So you're not going to receive the knowledge on how to achieve actually best performant algorithms, but you'd have still the idea on how to implement an algorithm which is concurrency driven. Then you could achieve parallelism in two ways, one which is actually called data parallelism, so which is actually used in any kind of scenario. Usually you have data and you have like the same set of operations. And then, given that the data might be like big data, usually the thing that you're doing, if the problem is embarrassingly parallel, so the thing that you can do is to split the data, run on each segment of the data the algorithm of interest, for then recombining the computation. So the preliminary step is called actually data parallelism. So you are achieving parallelism by running on different parts of the data the same algorithm. Otherwise, you have operational parallelism, which is quite different, which is I have the same piece of data, but I have a plethora or multiple operations that I want to perform, and therefore I'm actually using or running different operations on top of the same data. So these are the two different kinds of parallelism that you might see. But so usually in this module we're going to see the second bit, even though it might be confusing at first, but if you're thinking about that, you might to try and run multiple operations on one single machine. So that mostly reflects operational parallelism. That is what we're going to see in practice in this module. And then we need to study then what is actually going to run, which is actually the notion of a process. So a process that it is actually very language dependent. And here actually providing some kind of notions if you're also coming from a C or a Fortran background. Anyway, generally speaking, for the moment you have been using Java by creating like sequential programs, so without any kind of use of concurrency. In this case, the entire program is perceived as being the process. And then I'm going to provide like some graphical clarification of what's happening with that, which is just an instance of your program running inside the Java virtual machine. And then, as we're going to see, each program provides access to the resources in order to execute the program. So what are on earth these kind of resources? So for example, if you're accessing the file, you're going to have a file descriptor, so you have like one single point of contact for accessing the same file descriptor. So you have always the same mapping, the same file ID will represent the same file. You could have like the access to the memory. The memory is also a resource. Time is also a resource, so you're sharing the same time with whatever kind of computation that is going to be inside, and that memory could also be memory allocation. So those are usually the resources: time, space, and data, which is also space. So usually time and data will do as an simplification. And each process has an isolated memory, so what does that mean? So if you're running two programs in Java, they are residing in the same Java virtual machine, that's for sure, but you're going to have just the specific memory allocated for that program to run. So you cannot ideally access to the memory of another program. Then if you are hijacking the program, you could do that, but usually the operating system should have like protection measures in order to avoid this kind of hijacking nowadays. Nevertheless, we have a mechanism that we're not going to see, which are shared memories. So let's suppose that you want to efficiently communicate between processes without necessarily sending like HTTP requests to another program. Then you could create like a shared memory on top of which then you could directly share a certain set of memory on top of which then you could have the communication. And then you see that in Java, but that is just in Java, each process is started with like a single running component called thread. And in Java, you have that the process is already a thread, which is called like the main thread. So if you're just checking the Java program that you have done in the past, and then you're checking thread.current thread, it will give you the information concerning the process, which in Java is running on a thread. But what is a thread? Then actually the things is going to be more and more and more. So I'm going to provide like a graphical depiction of what I'm talking about. So the thing on the left is the usual kind of program that you have been writing so far, on which you have like a single threaded program. So the main program is one thread, and that one is actually the thread itself, on which you see the concept that I was trying to convey before, which are the resources that are shared. In here you also have something different, which is the code. The code is also a resource which is shared, somehow, yes. Because those are the instructions that are going to be run, then you have the data and the files. And then something which is specific to the thread are going to be the registers and the stack. What on earth is that? So I know that you didn't do like an operating system module, but just to clarify. Otherwise you have a running program that you cannot see what is actually happening. So registers are actually like the memory locally to your processor, where containing all the data which is required for some simple instruction to be run. So even though you're creating a Java program, let's suppose that you are running inside the Java virtual machine, so you have like a virtual processor which is running the instruction. Okay. This program will be associated with some registers which might contain, like for example, the function pointer, which is a program counter, sorry, which is actually saying which instruction is going to be run from the program, and it has some registers. So you're not going to read all the time from the primary memory or from the RAM. The thing that is going to happen is that somehow with some wizardry that we're not going to discuss because we didn't do operative systems, then the program knows which data from the primary memory is going to access, and this data is actually within the registry. So you could see that you have a very small RAM inside your processor. And that is actually the data that the processor will use. So you're not going to access all the time the primary memory because it's going to be slow for the processor. So usually you have registers and some kind of memory in addition to that. So that is the abstraction. If then you have different threads, then okay. And then the other thing that you have is the stack. The stack is, let's suppose that you have a recursive program and you're calling a function on and on and on and on. Then you need to remember from which point you'd have execution of the function and at which stage you were. So whenever you're going back to the previous call, then you have all the variables with the same value, so to speak. So in order to remember all the previous computations, you also have something called the stack. So given that all the threads could run different programs and could be at different points of executions, then you could have different stacks. So that's why registers could also contain information regarding like the instruction of the program where it's actually the program right now, or the stack. That's why each thread will contain separately that. So that is actually the idea that you see on the right, on which you have a multi-threaded program, so you're creating somehow, as you're going to see, multiple threads, and each of these threads are going to share data and files, so the primary memory and the files being accessed, but we're going to have separate registers and stacks, so to remember better the execution order of the program. And that is actually a very simplistic example. So, we'll stop now for a bit. So, do you have questions before I continue and show you this little example? No questions so far? Please raise your hand. Okay, yes.
That sort of like register you were talking about, you said like it's on the CPU, or is it kind of like in the processor, or?
Okay, thanks for asking. I will repeat the question for the microphone. So you're asking about actually the registers, where they reside. So those registers are residing within the CPU. So you could think about, let's oversimplify the architecture, and I'm not going to discuss the multi-threaded one. Just a simple, some simple architecture, back in the days, the thing that you can also find like inside a clock or something. Then you have registers, which are keeping track of the changes of the data, and they're also remembering the current state of execution of your program, and they are in the CPU. So the thing that would happen is that you're not all the time accessing the primary memory, so you could also do that, but that might be slow. So some of the data, but that is also dependent on the program and on how the program is compiled. So some of the data could be cached somehow within the CPU, so it's directly changing the data within the CPU, and then the outcome is pushed on the RAM. One example is actually the execution of arithmetical operations. So if you have a very long expression, 1 plus 2, open close parentheses, times 3 plus 5, then you might have that these numerical values are pushed as in registers. Then the CPU is actually running the values, because it doesn't make any sense to read those numbers from the primary memory or RAM. And then at the end you have a value, but the value is not still associated to a variable. So while you're doing the operations, those values might reside like in the CPU. Then you assign to a variable. The variable eventually will be accessed to a primary memory allocation, and then at the end you know that the outcome values associated to R, the compiler decides that it's going to be allocated at this offset in primary memory, and then you're going to have it. So you have temporary data, and definitely anything that needs to be fast access is going to be there. But sometimes you might have, like, if you have a linked list, for example, then you're not storing all the data inside the CPU. So you're just navigating that, and the only information that you are retaining if you're navigating something might be the pointers or something. So anything that needs to be fast accessed is going to be stored there, but what is exactly stored is going to be dealt by the programming language itself. So if you're using assembly, you're actually telling this should be like a registry variable, this should be on primary memory, then I'm loading from this primary memory and pushing that to the registry. So if you're programming in assembly, you know that precisely. Otherwise, you have an abstraction and everything is going to be dealt by the programming language and is going to decide what to do in order to optimize the program. Then Java usually does not optimize, but if you're taking, for example, C++, you have different optimization levels, and at different levels might decide to do something different. And so you have different assembly at the end. Does that answer the question? Okay. Any other question? Good. So in here, I'm also using some kind of lambda notation. You might not have been there. So why on earth I'm showing you something that is actually going to be something that you have not seen before. So actually, practically, there is going to be one reason. Because even the written exam, I'm going to ask you for writing a simplistic Java program. And given that there might be like the pressure of exam of doing something right, or people that are concerned about doing typos when they're writing, then I wanted to simplify the code writing as much as possible. So you could also create new thread, and then if you are accustomed with anonymous classes or anything of the like, you could say new runnable and then expanding that. But that is actually just to have a fresh start. So this is going to be like a lambda notation on which I'm saying that you have like an anonymous class which constructor is known and is taking actually no arguments at all, and you have like a method which is just going to be running something without necessarily returning. So I'm taking no arguments, and this method inside this class, that is actually the thing that I'm implementing or extending depending on if you have an interface or a class, is just doing system out println hello new thread. So that is actually what is that about. Then in here you'd have that you're running the new thread from the process, then you're starting a new thread. Very important, unless you're doing explicit. Okay, another thing that I was missing is this var. Maybe you're not accustomed with var. So also that is for helping you with exam. Otherwise you need to be redundant and say thread x equals new thread blah blah blah. So I know that for sure you haven't come up with like compiler theory or anything like that. But usually the compiler, a compile time could infer which is the type associated with the variable. So that is actually what Java is doing under the hood. So you know that you're creating a variable x associated to new thread, and new thread is actually the class. So automatically Java would know that x is of type thread. So var is just to say, I'm lazy, I do not want to create like a variable type, and I don't want to be as lazy to write objects, so I'm completely discarding the type information. I want to retain that, and I want the compiler to check that for me, what the type is. So doing var is also admitted. So in the exam, I'm going to provide examples where you might write var just as a shorthand for writing something. It's going to help, so you have like a pseudocode notation within Java itself. That after declaring the variable and creating a thread, creating a class is not making it wrong. Okay? So you need to actually start the thread. How would I do that? By using the start. So now I'm oversimplifying things a bit. You see that you have a throws exception there. We will clarify that sooner. But at this point, you could start the thread, and then you might want to wait the thread to terminate its execution, and that is what join is about. So in here is, are there any errors beside the typo errors written with 2s? No, in here there are none, but you might also have this kind of questions that I'm going to ask you interactively. Okay, so just to show you what I was talking about, so, if you see here, maybe the font is too small. Alt Shift. Okay. Alt Shift. Okay. So, can you see that clearly now? Good. So, this is actually the program that is written on the slides. So, let me show you. Now I'm commenting the start line, and then I'm trying to run this very simplistic program. It's going to build. Sorry. It's going to run the exercises for the model. Yeah, you see, if I'm not using start, then you have just running the main thread from the process, and the other println is not appearing. So that is an indicator that start is required for making the program run. It should be very simple to understand, but most of the students in the exam might forget that. So this is actually on the first line, or more, almost, so please remember this. On the other hand, I'm making it run, and now you have hello new thread. So that entails that by inactivating and deactivating this line, you're actually starting the thread which is going to print that, or not. Also, another thing that you're allowed to do is actually play or use the code as much as you wish. So the other thing is, I don't know what that syntax is about. You see, you have, if you're using the IDE and if you're doing Alt and Enter, you could also say, okay, what is that lambda about? Expand lambda to something. Oh, well, that doesn't help. So replace lambda with anonymous class. And then you have what that is about, you see? So I'm creating a new runnable, which is trying to override a method run, and blah, blah, blah. So that is what that lambda is about. But that is tedious to write, and definitely it takes time during the exam. So you could take like recent Java to just write all this jargon, and just to write replace with a lambda. So you just have that. That is for your convenience, and so you're not going to write like and spend and waste time during the exam. So that is also what that lambda was. But we're going to explain runnable in the following lectures. Any questions about this example? Yeah.
When you commented out the x.start line, the thread did not start, so shouldn't x.join have thrown an error or something?
No, good question. So we're going to see that the day after tomorrow. The join is just for waiting for the termination of the thread. So let's suppose that you want to create, for example, like a server that might run forever. Then you might want to, so you could also wait for that, but if you cannot care whether the execution is interesting to the following, you could just run something and then it will continue running forever. So join is just for waiting for the termination of something. But it's not a requirement to join, because that is just waiting. So an example might be when I might be interested in wait, it might be that maybe the thread would fail, and so it will throw an exception, and then when I'm waiting with the join, and catching the exception that the thread is throwing, by which I would know if something went wrong. So that might be a good use case example where I might want to use join. But, okay, I got your question. The thing is, why on earth joining is not raising an issue? Joining is just because it's waiting for something. If the thread has not started, then it's checking, has the thread started? No, then there is no reason for waiting for something. So that is actually providing the whole spectrum. Why is there the join, which is actually the purpose for waiting for something? Why? Because maybe an exception might be thrown, and I want to catch the exception and know what is happening. Well, why on earth then, going back to your question, waiting for something that doesn't exist, doesn't throw an exception, just because the thread has not started yet. And the only reason where you might have an exception is whether the thread was running and something went bad inside the thread. Does that answer the question? Okay. Yes?
If we don't have intelligence, for example, in exams, how to write the correct lambda function?
Okay. So I will discuss that in more detail when we're going to deal with exam. But the idea is how to deal with potential errors, and so given that I know that you are dealing with no IDE, then I'm going to assume that some typos are admissible. Okay? So I'm not expecting to be like spotless. So you might have some typos. The kind of errors that I'm going to look for are logical errors. So what if, so we're going to see the kind of exercises later on. But let's suppose that you need to force an execution order, and the way you are enforcing the execution order is not correct, then that is independent from the syntax of the code. So logically I would see, okay, I'm not a compiler, I'm a human, so I could understand what you meant, but still independently from the bug, the compiler bug, there is an issue logically. So the kind of errors that I'm going to catch and downmark are going to be logical errors on the understanding of the code rather than if the syntax is pointless. Does that answer the question? Okay, good question. But we're going to restate that as soon as we're going to find the exercises. Thanks for asking, by the way. Any other question? So eventually, as soon as we reach a given point, then I'm going to make a break, so you have like 15 minutes break, and you are more than welcome to come here if you have additional questions. That's for sure. Okay. So, I know that you also need distributed programming, but you have never encountered message passing. But that is actually a shame. So the thing that you could have if you have like a distributed computation is to do like remote procedure calls, synchronization, and communication as asynchronous communication. So when I was like a bachelor degree student in Bologna, it was very fun to create like fun in a certain sense, to create like multi-threaded program and to simulate message passing, like sending or receiving messages. So how could I implement a message passing protocol using concurrency implementation or vice versa? How could I achieve concurrency protocols using message passing? But that could not be done because that was not taught. So still, we might have a way to make threads communicate by sending messages, or better, by changing values to variables. So that is what we're going to do. So we're going to achieve then shared memory synchronization. So we're going to see, that is actually going to be the entire module, not today's lecture. Okay? Software-based or scheduler-based software, and those are going to be like kind of techniques that we're going to see to ensure concurrency. For now, for you, it's just a list of names. But hopefully this scheme is going to help you in know at which point we're at with the module. So I'm going to reprovide this schema all along. So that is actually the idea. So how could I achieve communication if I have message passing? Then, for example, each time you're browsing, you're sending an HTTP request to a server. That is a message that you're sending, and then as a receiver, you're getting the reply of the HTTP request. and that is actually a kind of synchronous communication. So if you are having no memory shared across processes, then the only thing that you can do, like your computer trying to communicate with another computer, is actually sending a message. And by message passing, actually you could achieve some kind of distributed communication. And that is one way. You could also achieve that in multi-threaded programming if you have one shared variable and you have a queue, like with a concurrency queue, and then you could also achieve communication by message passing using that. So, given that in here we're sharing memory, we could also have something more efficient. So if you just need to pass one value, then it might be not good to send a message, because the only thing that I want to send is just one value. So you just create like a shared access to a variable and to check the way I'm changing the values, and then I have shared variables. Then you start to see where the problem might arise. Have two programs that are trying to access the same variable, and they need to know whether that has changed or not. So there is actually where the concurrency problems start to arise. Then I think that, yeah, I'm going to stop after the definition of schedule, by the way. So, this is a notion which is theoretical, but understanding this will help to also understand what the program is doing. So what is a schedule, or schedule depending on if you're British or US pronunciation. So a schedule or schedule of the trace of several concurrent threads, T1, Tn, is a temporal ordering, what the hell is that, over the operations in each thread. So what does that mean? So it means that I have some threads, T1 up until Tn, and you could perceive in a very simplistic way that each thread is a linear program. So let's avoid to have like any kind of if branches, while loop. Let's oversimplify it to the extreme. So you just have like a sequence of operations. Simplistically, they could be just read and write. That will do. But what I'm reading, what I'm writing, who cares? Still have a sequence of instructions. Then, a program is an ordered sequence of instructions. Because if you're changing the order, then you're changing like the output of the program itself. So actually, it's important that they are temporally ordered, because that creates a program. If you're changing the order, maybe you're also changing the outcome. It's not necessarily the case, but generally speaking, it might. So then the idea is what happens when you have T1, Tn running at the same time. So I have all the instructions for each program. So I have like in a given thread K, I might have instructions OI and OJ, where I have that the OI instruction always precedes OJ. Then I have, when I'm running my concurrent program, this order is always reflected. So the thing that happens is that it's not because you're running a program concurrently that is going to shuffle the order of instructions. The order of instructions is going to be always the same. It's just the, so if you're taking, that is the idea, if you're taking one line and you're putting all operations in that line, so mimicking like with multi-programming, if you have just one thread, for example, and you're trying to use that single thread to run concurrency, then you'd see, if you're just focusing on the operation of one single thread, that if you're avoiding all the other operations, you'd see the same program all along. So the only thing is that the order of the instructions across programs are changed. So you might have the first instruction of the first program happening first, or the first instruction of the last program happening first, but you're just focusing on one program at a time and you're reading those instructions in a line, then you'd see that the order of instruction is reflected. So that is what that means. It's just a concise way to tell the thing that I told now verbosely. So this means that the trace is a sequence of time-oriented actions, and that is important. But still, what does that mean? This is actually another example, which is also provided in the slides and in the code. So, what is a good graphical depiction of instructions of a program is actually a lattice. If you don't know what a lattice is, you could also say that is a graph. That is fine. So, the thing that you would see graphically, let's talk about the program first, which might be easier. So, in the right, you have two threads that importantly are start and joined. Okay? And you have two threads, one writing A and B, and the other one writing 1 and 2. Then, if you take like the program linearly, that should be just A, B, 1 and 2. I also have a whiteboard. Then, what is all the possible combinations of a schedule that is provided by this lattice that you're seeing in here? So, under the assumption that all the programs will start at the top, and the ends of execution will be at the very bottom, then if you are traversing this lattice and you do all the possible paths, that will give you all the possible combinations of scheduling order of your program. And that is actually when the problems might arise, because the scheduler is not enforcing one specific way of running the program, but anything will do. At this stage, the only thing that the computer knows is that you're running something concurrently, and then any of these orders will do. So, you have print 1 and print 2, print A and print B. The thing that you might achieve is running all the first thread first, and then running the second, so you could do print 1 and print 2, and A, B. Or you could also have print A and then print 1, and then print B, and then print 2. Or you could also have print A, print 1 and print 2, and then print B, and so on and so forth. Also, this is reflected by the other program that I was opening before, which is slide 17. So if you're opening the program, which is slide 17, in here actually you have two programs, one doing A and B, and the other one is actually doing 1 and 2. Then I'm actually doing some kind of other finicky things just to change the order of execution, and to add diversity. But basically the thing that would happen, you'd see I'm running the program 1,000 times. So sometimes you might have A, 1, B, A, B, A, B, A, B, A, B, A, B, A, B again. 1, 2, A, B. You have another scheduling order. And then I'm sure that you might also have something on the lines of A. Yeah, and then you have another program which is A, 1, 2, B, and similarly you could also have because I copied the one. What a shame. Okay. And then you could also have A1. You could also have A1, B2. So if you're double checking, this program will actually output for you all the possible scheduling orders. So that's why it already indicates you somehow that whenever you're having specific problems, then it might be important to get a specific ordering of operations. For example, if I want to write a variable, then read the value, you might need to enforce a specific way to do the operations. But we'll see that after the break. Then I have some definitions that are also important, so please bear that in mind. So we say that the schedule is complete if actually S lists all the operations for all the threads. That is when a schedule is complete. That is in lay terms. But formally, it's complete if operations in S are exactly those operations, B1, T, and including a commit or abort. but we'll see that later on. So whether the program exits good, commit, or bad, you have an abort operation as the last operation of each thread. Then we say that a schedule is serial if for each thread all operations are exactly executed consecutively. So what does that mean? Schedule, just to have like a serial way, is actually, if you're taking just the edges of this lattice, then those edges like print 1, print 2, AB, or print A, print B, and then 1, 2, are serial because they're just running one thread, completing that, and then running the second, completing that, so on and so forth. So it's just having multiple sequential programs. So that is what serial means. And it is called serializable if it has the same final state as a complete serial schedule where all the operations perform a commit. What does that mean? So at this stage, so you need to think what is final state or state of the program. You could think like if you have variables in your program, the final state are the final values of the variables. So that is your state of the program, the values resulting in that program. So in here, I'm just printing something so any order would do, but as soon as you want to do like a specific mathematical operation, then the order becomes important. Then you need to do like summations before multiplications or vice versa, depending if you have parentheses or not. So, and that is going to be relevant. So at that point, then the program order becomes significant, but if you're just having print, then any order will do. So that is actually when it's going to be serializable. So in here, you have an example just to ask you a question, and then we'll have the break. It's for you. So in here, I have two threads that are starting, and I have read and write operations. So as you see, I'm changing the variable of the variable of x, and in this occasion, I'm just doing like an algebraic sum, so either a minus or a plus, or changing the order. So, is this schedule serializable? So first of all, is that serial? Is this, yeah.
No.
Why?
Because one of the threads doesn't run to completion.
Good. So I'm just repeating the schedule is serial because one thread has not completed. But is that serializable? Hint, I'm just doing an algebraic sum. I'm seeing nodding, yes, it's correct. So it's also serializable in this case because given that I'm just doing an algebraic sum, then those two operations are interchangeable. If it had like a multiplication, then yeah, we might have something else. Yeah, and in here definitely you have the example that I was talking about. So these are two examples on the left of serial scheduling, because as your colleague mentioned, one process is entirely computing and that is actually going to commit. And the other one on the right is actually non-serial, because you see the thing that is happening, even weirdly enough, is that given that I'm reading the variable at different times, and then you need to assume that the x after the read is just a local copy of the thread, for example, then at this stage, the local copy of x is going to have a different state, and therefore one is doing over n, and the other one is going to do plus m, and then the other thread is going to write its local copy to the primary memory, and the second thread is going to write its local copy to the primary memory. So the updates of the first thread will be completely shaded by the second one. So in here we're starting to arise issues. with a scheduling order. So not even because the operations are not an algebraic sum, but even because I have like a shading problem of the values being rewritten. And the similar problem we also have in here. You see, is going to be the same. Even in here, I have an algebraic sum, but I'm reading variable x before it. So this is an abstraction. Okay, it's not like Java properly. But that is the kind of exercise that we're doing at the very beginning to understand the kind of problems. So I'm reading a global variable x, so then what does that mean? And then loading that in a local copy of x. Then I read the same variable. Then I have x, which is decremented by n, and then I'm updating the value in primary memory. And then the same process has the value on the cache or like on the registry, and then it's doing the sum and then writing that. So even in this case example, you have the code is non-serializable because this actually arises problem because you don't have the same output that you're expecting from an algebraic sum. And you just have like either the plus or the minus. And then you might ask, why on earth is that happening? First, yeah, so the problem is that you might have a local copy which is not updated to the latest value that has been written. And how do I avoid that? But then that is going to be discussed after the break. So I'll give you like 15 minutes, and then after the 15 minutes, we're going to continue with the lecture.
Hello.
Hello. Sure. No worries at all. No worries.
I have a question.
Sure.
In lecture, you said for lambda function, we can use the tubes in intelligent. So how to write lambda function by myself?
So yeah.
Without the tubes.
Without, sorry?
Without the hint of intelligence.
So the idea is IntelliJ is already suggesting you where to use lambda functions. So
I mean without the suggestion.
But the thing is, the exercises are going to be, as we're going to see, very schematic. So, for example, when creating a thread, so let me say, you are not required to use the lambda function. Okay, it's not a requirement. It's just something for helping you in fastening up the write-up of the code during the exam or during the coursework. So, if you are more accustomed or you are better with not writing the lambda function, that is also good with me. Okay? If you want to use the lambda function, then it's going to be very, how to say, straightforward and easy in this example. So whenever you're creating a thread, this thread usually requires to say which is a runnable, and you need to provide like the runnable task. This runnable is an interface which has as the only method run, for example. So given that you have this annotation being a functional interface, Java knows that that could be interpreted as a function taking no arguments and returning nothing. And that is already mapped into a lambda function within the language. So the idea is going to be that the thing that I was doing before, yes, is this one. So you could say new runnable and then running something in there, like hello world or anything, or you could write equivalently this, which tells the same stuff. I'm taking no arguments, and then this is actually the body of my lambda function. So you see, if you're going to write this in the exam, it's going to be fine, but you're taking more time to write everything. If you're writing, on the other hand, this one is going to be shorter. So at this stage, you might advise to use that in this regard. So instead of creating new runnable and then using it, you're just writing this. But it's completely up to you. If you do not want, if you're worried that you are not sure of something, then you could always write that. That is okay with me. If you want, you could also write that. That is actually one use case example, but it is not the only one. But for the moment, that is one way to use the lambda function. So it's just like we say that in English, syntactic sugar. It means that it's just a shorthand, or you're writing something faster. It's like when you're writing in Chinese, you're not using, like when it's printed and you're using calligraphy. And when using calligraphy, you're actually using another way to write, which is not like when you have a printed book. It's actually the same way. So that is called syntactic sugar. You're just writing something for taking less time. Okay?
If I have parameters,
Yes.
So I write it in the bracket.
Yeah, so that will be something like, another thing is, so if you have function, you see function is a functional interface, like an interface taking a type and returning something else, and it's still a functional interface. In this regard, you're applying T and you're returning R. So let's suppose that you have something like this. The thing that you could say is actually function. I take an integer, for example, I want to return a string, and that will be my x. Okay. Then the thing that you could do is to say that I have an integer of s, and the thing that I'm returning, with this thing, and then return s to string. This is an example of a lambda function taking one argument, like the s, and returning that as a string. So you could use this syntax, or similarly, you want to use like an anonymous class, then you could say new function, integer of string, apply this. But you see that it's going to be like slower to write. If you have an argument, then you are just replacing with a lambda. Even shortly, you could write like that. So it's going to say I'm just taking s as an argument, and I'm returning the string. But you could also further simplify in Java, saying object to string. But it's completely up to you. So you have a lot of ways to write the same stuff. The important thing is actually something that you're confident with. Any kind of style is fine. So this style, this style, this style, this style. They are all the same, just completely up to you what you want to choose. Okay? No worries.
Thank you.
No worries. No worries. So we're going to start in 1 minute. Okay, so let's start. So at this stage we're going to start looking at the surface of shared memory synchronization. So the aim of the entire module is going to be how to deal with this kind of inconveniences that we were seeing before, so to force the execution of the program, of the multi-threaded program, in a given way that gives us a satisfactory answer. And that is actually the purpose of everything. So, and we're going to simplify that the communication happens through one shared variable, and we want to enforce like a specific order of operations. So how could that be enforced? Well, simplistically, even without discussing multi-threaded programming or specific kind of constructs, you could also have specific classes in Java, which are the atomic classes. So what are those about? So my suggestion is also to look at the documentation. So the thing that you could say is actually you're just hitting the shift 2 times, and you say atomic, and then you have atomic big integer, atomic reference, and then you could also have a look. If you're control clicking on the package, for example, atomic, you have all the classes that are atomic. You have atomic boolean, atomic integer array, so on and so forth. So those are pre-built classes made available for you for ensure concurrency while accessing one single variable of a given type, on which you might have like pre-construct operations like increment, decrement, multiplication, so on and so forth. So one very simplistic way is just to use these classes. Then what if we want to do something smart, like for example, we have the simple usage example is that you have a relational database, or you have like concurrent transactions on which you want to enforce that some kind of operations are going to be done independently from, say, the order of execution is dependent on multiple variables rather than one single variable being concurrently accessed and mitigated. So you have like interoperations between variables. So those classes are not helpful anymore. So that's when you need specific constructs. And one very simplistic way we could do at the very beginning, even without any kind of knowledge of Java, is using like the strict two-phase locking. So you have something called a synchronization protocol, which is going to be like strictly determined by some series of laws, to which you need to abide by, and those are ensuring the concurrency order. Well, I'm saying that because then you could also have a look at the code, and then you would see why on earth I need to do this specifically, cannot achieve the same stuff by doing something different. Then the answer to all these questions is yes, but that will not be abiding by the strict two-phase locking. So those exercises are precisely on if you're able to understand a procedure to apply to achieve concurrency control. So it's just like a protocol, but you need to enforce. Beforehand, so let's discuss the first kind of construct first. So let's suppose that we have a way to enforce atomicity. So we call that an operation is atomic if it can be run to completion in one go or have no effect. So what does that mean? So it's similarly to when you're doing like a transaction operation. So the easiest example is you're trying to do a payment online, something goes bad, and then if something goes bad with internet connection, then you have no money subtracted from your bank account. The example is actually the ATM. If you have poor concurrency problems, you might have two different kind of poor algorithms. One where you have no connection with the ATM, and so you have the thing that is advantage for you but not for the bank is something goes wrong, you're receiving the money, but the bank doesn't receive the feedback that you want to withdraw the money from the ATM, and so you have a problem. The completely opposite problem is you're not receiving the money, but the bank is actually going to detract from your account the amount of money that you're trying to withdraw. You want to have neither of these two operations to happen, so that's why you need to ensure atomicity. And atomicity ensures that if something bad happens, then it's like nothing happened at all. So the other thing is, what is atomicity atomic per se in Java? So in Java, something is called atomic, an operation that you could fit in a word size. What does that mean? So, what is a word? Nowadays, you have most of your PCs that are 64 architecture. And so, that is the size of the word, 64. Older computers have 32 bits architecture. So that was the size of the word. Then you had the very first computers that didn't have even a bit or a byte size. They have different kind of systems. But anyway, the word size is the operation that could be run atomically in the processor. So one thing, just to give you an understanding what that might be. Let's suppose that you're reading data from the primary memory into one of these registries in the CPU, and then you have like the buffer or the bus where it is transiting. And let's suppose that you just need to run one variable. In a very simplistic assumption, then all these operations in one tick of a CPU clock, you're just reading one instruction at a time. Let's suppose that might also happen. So that is actually the word size is the size of the operations that could be run atomically because they could be done in one CPU clock. So in one clock, I'm reading one variable and doing that in the registry. In the other clock, I'm reading the variable, putting that in the registry, and then I'm doing the operation. So if everything is within the word size in one clock tick, I could read this word, like for example 64 bits, and then I could do an operation on 64 bits at a time. And so if you have a variable and you're doing operations on 64 bits, then you're ensuring atomicity by itself. If otherwise it exceeds the word size, so for example you have a long, or like you have a long variable which is 64 bits in a 32-bit architecture, then that is actually a use case example of something exceeding the word size, and that might require multiple clock ticks to perform the operations over 64 bits. So for example, long variables are not atomic on 64 operations. And why that might be so? In multiprogramming, definitely you might have a context switch, so you have one program running, the stopping, and the other one running again. And so you have like an operation that is trying to do on one variable, but you haven't finished that. And then the other process, when you're starting to run, would see a dirty value, as we're going to call, so a not complete value, and it's going to read that. That might be might be a problem, so we want to ensure that then when the other processor is reading something, is only reading the final value, not something that needs to be updated again. And definitely that might be also happening in multiprocessing because you have multiple threads accessing the same variable, and maybe you haven't read the last value that you're interested yet. So you see, all these problems might arise independently from whether you have multi-threading in your PC or not. So, okay, let's do like in this way. So let's suppose that you have an increment operation on like on a word size. So an increment operation means that simplistically, I'm not going down to the level, I'm incrementing the value by 1, for example. I have a plus on one single variable. Is that atomic? Even though we are in a 64-bit architecture and I'm using like an int, which is not 64 bits but 32. Is that atomic? So is the increment operation atomic by itself? Why not? So the other question would be how many operations are required to do an increment in terms of read and write? Is just one, or are we actually doing more than one? Yes. Which are those?
Is it the event like replacing the values as well? Like the event like base equals like for example 5?
Okay.
Like having a temporary value and then kind of like removing the temporary value?
Yeah. So definitely good answer. Very good answer. Definitely have this kind of operations that you see here. So definitely first you need for variable x. Then you need to increase by 1, as you were saying, for example, a temporary variable, and then you need to write to the memory. So given this, then the increment operation is not atomic. So it's not that if you have like a word size variable, then if you're just doing like any kind of operation, it's going to be atomic per se. Because maybe you're perceiving something as atomic in your program, but that single instruction is actually written in assembly level into read, increment, and then write. So it doesn't seem atomic. So that also goes beyond the memory. So it comes from guarding the program itself, so to ensure that the execution itself is atomic. And that is actually the explanation. So I could have a read operation and then a write operation. And that is actually the syntax that I'm using. So even in the exam, you could use R of I, it has like the thread number I, which is doing the read operation from global variable x. And WI means that I'm doing a write operation on the variable x. Is that clear? Questions on that? So, going back to, that is actually the thing that I was discussing before. So that's why in this, for example, in atomic integer, you have already some operations that are atomic. So usually in concurrency theory, you're using this kind of angle brackets to say that an operation is atomic, so to ensure that everything is done in one shot. So get is just reading a value and potentially reading that value into a temporary variable. And then you have increment and get that might be you're incrementing by 1 the value, and then you're reading that from the global variable, and then you're returning that wherever that is required, or reading the value from the global variable and then incrementing that. So you have that as atomic operations. So at this stage, you might completely forget how those are implemented. It's just to get you started with the notion of being something atomic. So everything that might be of interest at the moment is just you have specific instructions that might be implemented atomically. Then you would see at the end of a module that how we could implement an atomic operation, but it is not of our major interest right now. So then you have like hints of exercises. So investigate the other methods on the package or investigate the other classes from the package. So if you want, you could also just do as I was doing before, that you are basically checking the atomic package and then you have all the operations that you might come up with. So I'm not doing like the tutorial or like the reference manual. So I'm expecting you to be sufficiently curious to look at the manual or to the library itself, so to know which methods might be useful later on for the coursework or for the exam. So those are provided as exercises for that reason. Where is the good pointer? Yeah. So now we start to discuss what is a conflict and a data race. Those are synonyms, so they mean the same thing. So that is actually the definition of a conflict or data race. Two operations in a schedule are said to be in conflict if they satisfy all of the three following conditions that potentially leads the process into an inconsistent state. So I'm just slavishly reading everything, and then we're going to discuss those. They belong to different threads. They access the same shared variable, or at least one of the operations is a write. So why do you think that might be the case? So let's try to take only one of these operations. They belong to different threads. Okay. They could also have multiple threads, but all these instructions might be read operations. So what about that? Do you have conflicts or data races? No. So that condition alone is not sufficient. They access the same shared variable. Yeah, But if you're doing just read operations, then that's fine. Even the beforehand is even more general. They have concurrent operations but on different variables, so what about it? No worries at all. The second one is providing some kind of restriction. What if they belong to different threads and they're accessing the same shared variable? As I was saying before, they could always be read operations, so what about it? I don't have any kind of problems. I'm just reading, like, for example, a log. So that is not the problematic. The problematic part is the write operation itself. So if I introduce the thing that at least one operation is a write, in addition to the prior two conditions, then I have a problem. But even having the write by itself is not problematic. What if I'm writing a variable, but I have no concurrent threads, like I'm violating the first assumption? Then I could also have multiple writes on different variables, but I'm not having like a concurrency problem. I don't have any kind of over operations, and that's fine. So you see, the idea is you need to have all of these three conditions in order to have a problem on concurrence. So that's why theory is important. Otherwise, from the actual program, you are not going to perceive the nature of the problem itself. Therefore, the theory helps you understand what might happen, and then you need the practice to put that into practice. So that's why I'm dealing with these kind of things in this way. So, given this, and given that the write operation is the cornerstone of the problems, then we might just have three kinds of conflict, so to speak. Write and read conflict, read and write conflict, and write conflict that we're going to discuss now. So, write and read conflict. What is that about? So, this is an example where it's very similar to the things that we've seen before. So in here, I'm doing an algebraic sum. So if I was doing these operations in a sequential way, that should not be problematic. They always lead to the same final state. But the problem is that the first thread is completely doing a read, subtracting the value, and then writing it. But in here, it's also important to have a commit. So ideally, as we will see later on, commit is the command on which say everything goes good, then write the value to primary memory, so to speak. If you have a remote transaction, it's to say, okay, now I want to persist the operations inside my database or what have you. So the write operation is writing, is saying, okay, I want to commit the operation, so I want to write to the global variable. But not yet. Commit is actually the thing performing the write operation. So that's important also to mention. If you have an abort, then I'm completely not updating the shared variables. Then at the other stage, I'm doing a read operation. So given that the other side has not completed yet, it's still reading the previous value, so not the decremented one, sorry. Then I'm incrementing x with the previous value, even the same value that t1 is reading, and then I'm writing, and then I'm committing. And here the problem is that, for example, I have, in this scenario, I have a write and then a read problem. So you might also have a different kind of problem that we are going to discuss later on. But in here, most importantly, you have one issue, which is a write-read conflict that entails that you're writing a value, but then you're reading it, and potentially, let's go back, let's recap. So the issue in here is different. I'm writing the value, and I'm updating the shared variable, Then here, I'm doing the read operation. Yeah, that is the correct answer. And the read operation is actually reading a value which is unknown whether it's going to be committed or not. That is the key. So, given that I'm reading a value that might be updated or might be not the final one, then I have this kind of problem. So, sorry, let me rephrase that. So the issue with T2 is actually reading the value from T1, and the value from T1 is actually not committed yet. So I don't know whether the value will be like the final one, and so I have a write and read conflict. So let me rephrase that again, just to clarify. So the notion is I'm reading a value being updated by T1, but I don't know whether T1 will commit or abort the operation. So the problem is I'm reading a value that might be stale or aborted. So I need to ensure that whenever I'm reading something, it's going to be the last word of the process itself. So that is going to be something that I want to read. So similarly, okay, that is actually the explanation. So what if I have an abort operation? If I have an abort operation, then I know that that read operation shall never read the value that has been written. So I have a write operation, but that write operation should not be effectful up until I'm aborting. So that entails that potentially you shall never do a read straightforwardly after a write operation if I don't know which is going to be the final state of the program, whether that will terminate or not with a failure. So that's why then we need to introduce a scheduling order, so that's why we have restrictive phase locking. Yeah, in here you have a read and write conflict, which is actually the thing that I was saying before. So in here actually you have the other scenario with the read and write conflict. So sorry about the confusion. So in here you're reading the value of x before any kind of update. And so you're reading the same global variable. And then once you're actually providing a write, and then you see the order of execution is shuffled, and so the other value is still reading the previously read value, so I'm not going to read the update from thread 1, and then I'm writing the same value after the update. So, and then I'm committing, and then the other one is committing to. That is going to be committed dependent. So here the issue is that I'm reading a value which might be stale, so old, and then I'm providing an update which is ignoring the update provided by the other step. So even here the issue is reason, because I'm doing a read operation and then another one will do a write. So that intuitively should say that whenever I'm doing a read operation and then someone wants to run the same variable, I should also block this possibility. Because I need to protect the data that I'm trying to read now from anyone else. And still, you also have a write and write conflict, which is somehow similar to the previous cases that we were discussing. In here, we have a write and write conflict because both are reading the value, but, how do you say, you're having a write operation, and another write operation might change the state of execution. So in here, I'm doing the write, and then I'm doing the other write, but the second write is not taking into consideration the updates of the first variable. So in here, the conflict does not arise at the read level, but at the write one. So I know that in here, you might have multiple interpretations, so it might be ambiguous, but even in the exam, it's going to be clearer what kind of conflicts you are going to have. So in here, there might be multiple interpretations, but bear with me. The idea is the kind of conflict is just between write or read and write, so that is actually the first signal. The first kind of problem that appears. So in here, there might be also a read and write conflict, so that's why it might be ambiguous. But the thing that I want to stress here more is actually this write to write. As you see here, it's not necessarily a read and write conflict because the operation on the X is done before the write, but still it might be confusing during the exam. So I'm going to be as less ambiguous as possible. In here, I provide the motivation why that is not a read and write, but it still might be confusing why is not a read and write conflict. So this is actually the motivation as I was saying before. Because an operation of the X is done before the write. So you might but it could be still a read and write problem, but it's not necessarily the case, and here is purely a write and write conflict. So that is actually the same write and write conflict, but where I'm doing first the first write and then the second one. So one of the two updates is going to shadow the second. And so in here, I'm going to skip on those quickly because it's just a better notion, so because everyone has a different way of thinking about stuff. So the same kind of conflict could also be phrased differently. So you have lost update, dirty read, not repeatable read, or phantom, which is a slightly change of inconsistent read, which are going to be actually the same as the thing that we discussed before. So also those are synonyms. So if a lost update is the same kind of stuff of write and write. So it's just providing like a mini explanation of why write and write are an issue. I'm losing an update. Either in this way, write one and write two, or vice versa. So with a write one and write conflict, I'm going to lose some kind of information nevertheless. A dirty read is when I'm doing the write, and then I'm reading the same variable, and the issue that is, I'm reading a value that might be not the last word of the process, because you need to abort, and then that actually violates the good practice of actually reading what should be the last word. And then you also have a read and write conflict, on which I'm doing exactly the opposite. I'm reading the value, and then a write operation is going to happen next. So the read operation might read a stale value, stale value, which is going to be outdated nevertheless. And so I might, T2 might have a variable which is not updated. And that is actually a problem because then I'm not ensuring and not taking into account the previous execution. And then I have on the right, which is just a graphical depiction of all the stuff that we were discussing before. So on sequential execution and interleaved execution. So a sequential execution, as we were discussing before, is one thread completely runs, and then the other one will stop, and then it will actually make thread P run, or T2. And an interleaved execution is actually having multiple places of the same program running along. So the idea is that those might happen, but we're not sure what will happen because the scheduler might decide freely the execution order of a program, so you can predetermine what that is going to be if you're not ensuring concurrency control. So the idea is somehow we need to exploit some kind of mutual exclusion that prevents, so what does that mean? So we want to prevent that certain operations are going to be performed. So if I'm accessing one variable on reading, then I want to prevent another process to write on that because, for example, there might be some kind of issues if I'm reading a value that then is going to be updated, and then I'm having like old information. So I want to avoid this as much as possible. And then you might have like conditional synchronization that might be seen at the end of the module, so by the end of this week or the next, on which we might wait on a specific condition and then leave another process to continue, because we could continue to run even within this kind of mutual exclusion, only if some conditions will be met. But we will see that later on. So we want to exploit this kind of mutual exclusion to avoid any kind of troubles when running. So that's why you have something which is called shared and exclusive locks. So let me give an example first, and then let's discuss what those locks are. So let's suppose that I'm writing on this whiteboard, and then I'm writing, and then there is actually another person writing. And in a very simplistic example, both of us are actually going to write at the same time on the board. In this way, I want to prevent this to happen, but the other thing that I want to prevent happening is that you could start to read from the board if I'm not sure of what I'm writing. So let's suppose that I'm starting to write and I need to cancel something. So the thing that I want to do is try to block you from seeing the board up until I'm sure that everything that's written is actually what I mean for you to read. So that's why you have two synchronization mechanisms. one is going to be exclusive locks, and the other one is going to be called shared locks. So an exclusive lock is always, or shared locks are always associated to one single variable, global variable. So, for example, in here, A. So the thing is, if I want to have an exclusive lock, then it means that this property is all mine and not yours to use, and so I'm preventing anyone to access that. So neither a process trying to also acquire an exclusive lock could access the variable, nor another one trying to have a shared lock. So that is usually, as you might think, associated with a write operation. So I might want to admit only one operation at a time. But what if I want to read? So all of you are acquiring somehow a shared lock of a variable, because if someone of you is reading, it should not prevent another one from you to read as well. So I want to just say, please, teacher, professor, what have you, do not start writing because we're still trying to read, and if you're coming to the board and start cleaning, then we haven't finished to write whatever was written on the board. So by acquiring a shared lock, you're saying, please do not erase the board or do not add something else, otherwise you will not be able to read what you have written. So that is actually what a shared lock is about. So it's just to say everyone collegially is reading from the board, they just finish to write, and when the last one of you will terminate the reading, then I will have automatically the possibility of acquiring an exclusive lock and start cleaning the board or writing again. So that is the intuition behind shared locks and exclusive locks. And the good part is that those are also enforced within the strict two-phase locking. So why is that called strict? Because you also have a relaxed version of the algorithm itself, but we're not going to discuss that in better detail because they are just concurrency theory from database. So processes must ensure that there are no conflicts and aborted transactions. So what is the protocol for security for that? So write operations require the use of exclusive locks. Read once use shared locks, as was mentioned before. So exclusive lock, I'm just saying that is actually my property now, my treasure, and could only have access to the board. And then every one of you that is reading, then they could share the same resource. But that's why all the write operations are going to be accessing to write operations, and all the read operations are going to be used with that. But I want also to avoid me locking inside my lock. So let's suppose that you're locking on reading, and then I'm asking you to come to do an exercise, then you're starting to write something on the whiteboard. After doing that, then you are acquiring the shared lock. But you want also to enforce that you're not locking yourself in a state where you're both reading and writing, so you need also to remember that somehow. So how does the protocol guarantee this? Has an assumption that they already know which are going to be the set of instructions that are going to be performed. In this case, now you have a query, you're sending a query to a relational database, so they know whether you're updating the database or not. So the database itself receives your query, they know what you're doing. So they know what is going to happen, basically. And from that, then they could decide which is going to be the lock. So if you have transactions with different objects, then they are completely interleaved, so there is no reason to ensure any kind of strict two-phase locking. And if at least two transactions want to handle the same object, then you need to ensure seriality of the program itself. And that is actually the protocol. And it's quite slavish in the way it will be applied. So in the exam, you're going to have one exercise of schedule or scheduled that might have an issue within that, and then you need to change the programs to actually achieve the strict two-phase locking. So for each instruction, for each thread you're doing in this way, if X was already accessed in the past, do nothing. Why? Because if that was already accessed in the past, then it already applied either a shared lock or a exclusive lock. Otherwise, this is actually the first time in this instruction when I'm accessing the variable, then I need to check whether in the future, anytime, I will use the write operation. So it's like saying the student, anytime, would come to the whiteboard to write. Under that occasion, then that is why it's strict, because anyhow, I'm not releasing the lock and then putting like a shared lock. Slavishly, I know that in the future I will always do a write operation on the variable, so even though I'm doing at the very beginning a read operation on the same variable, I'm always acquiring an exclusive lock, always, because in the future I will be writing. Otherwise, if x, the same variable, will be always accessed in a read operation, then I'm just using a shared lock on the program before performing the concurrent operation on the variable x. And then at the end of the program, I might either have a commit or an abort, but that is actually strictly related whether the communication goes bad or something like that. And here, very simplistically enough, we might have that we are enforcing always an abort or a commit. And that is the only phase where all the acquired locks for the mutual exclusion are going to be released, and very importantly, they're going to be released in the inverse order of application. Why? Because if I was accessing variable A first, and then B second, and then C next, then I need to release the C first, and then the B, and then the A, because in that way, then I'm ensuring the correct order of application. It is like when you're having a program with blocks. So first you are closing the last block, and then the second last, and then the first, in the same way. And that is just a protocol, so it's just a lavish application of this. And that should be, I think, the second last slide of so. So, that is already, you see, after this lecture, you could also do already an exercise for the exam. And that is a kind of exercise you could also train upon. So that's why I provided this at the very beginning. This kind of theoretical part gives you an understanding which are the problems of concurrent programming. And even though you don't have like a good understanding yet of how to achieve or ensure the problems, then you could always have this kind of read and write locks that are helping you in achieving a good execution order, without using any kind of constructs that we're going to see next. So how does that goes with Java? So let's suppose that all the threads are going to do the operation on the top. So I want to exclusively access variable A, that is already the final solution of the exercise from the example anyway. Then I can read A, write A, because you see I'm accessing write in the future. So even though the first operation is a read on read on A, then I'm always using a mutual exclusion. Then given that B will be only accessing the reading, then I'm doing S. Then in the exam, you're going to have the same kind of text about without the X's and the S's. So you'd have to provide the shared or exclusive locks if required. So how do I achieve that in Java? Well, in the newest version of Java, you also have the possibility of implementing directly this kind of string-to-phrase locking, because you have where entrant, you'll see that what that means later on, read and write lock, which are actually doing this for you automatically. So as the protocol says, you need to create two locks for each variable being accessed. So you have read and write lock for variable A, another one for variable B. And then you have a volatile, which we're going to see later on in the modules, as soon as we are going to deal with that, mimicking some global variables. Then, what is actually the exercise? So in the exam, you have, but we're going to see the exercises later on, during next week. Then the exam exercise could be, I want to fix the program just to create the shared or exclusive locks, and then what if you're not understanding correctly the logical part and you understand Java better, then you have like some other points for showing how that on top is actually done in Java. So what about that? Then that should be like thread 1 and 2. Those are actually the things that are going to be required. So one thread will just obtain the lock. So it will be like x of a. And then all the time, the thing that I'm doing is, first I'm reading the value. So that is R of a. I'm reading the a into a local variable. And then I'm doing some local write operation, still locally. Why? Because that is important to ensure atomicity. So I want to write the value only at commit time, because if I'm aborting, I do not want to write the shared variable. Okay? So that's why the write operation is done locally and not globally by implementing the protocol. And then I know that I'm going to read variable s, so I'm just using the same value in the local variable. And then you see I'm unlocking the b. And then after that, I'm updating the global A with the local variable, and then I'm also releasing the lock. And also that is important, I'm releasing the locks in the reversed order. So I will give you the opportunity of also changing the program. What if I'm changing the program like that? And then they give you opportunity of doing so. And then the other question is, what is the effect of changing the program so to have locks? The thing that we discussed before. Let's suppose that you have a mutual exclusion. You could freely assume that you have always an exclusive lock. And exclusive lock is like having a lock in this scenario. So what locks are doing, let's go back to the very first beginning of the slides. They are forcing the execution order of a program. So if I'm adding a lock, and we will see that later on, for each thread, the thing that you will see is that you're enforcing a serial scheduling order on which, depending on which thread is able to acquire the lock first, then the thing that is going to happen is that the first thread that is going to acquire the lock is going to do all of its operations. So the first one starts first, so you're having A and B, and then you're unlocking, and then after the unlock, only after that, then the process 2 could acquire the lock and do 1 and 2 operations, and then unlock it. So that is actually the intuition, and then at the end, you always have a serial and serializable schedule. So that is what graphically it implies having locks. So you're forcing the execution order so to be in a specific way. Then you can also provide the same diagram if you have read and write locks as we were doing before. So sorry about that. I forgot also to mention what are read and write locks. So in Java, read lock is a shared lock, so it's acting like an X. It's acting like an S. Sorry. And the write lock is an exclusive lock, so it's acting like an X. So they are just named differently, but they're doing the same thing. So that's why you could directly use Java. So my suggestion would be, even when you have exercises for the exam, and then you need to apply shared lock or exclusive locks, then you also have a way. This is a theoretical exercise. I don't know how to apply that into practice, but then I give you the tool to also show in practice how something is working beyond the theory. So the idea is, I'm always going to give you theoretical things and how to implement that into code, so you could also test the exercises by yourself, basically. And in there, I'm just providing like a set of exercises, but it's just for you to engage and investigate yourself. So then we're going to have a practical session on the afternoon. You already have the coursework, but if you want, you could also go to the intermediate exercises or just do this. Any kind of question before the end of the lecture? Yes?
The coursework for this module is due the 10th?
Yes.
Oh, okay.
I'm afraid so. So it's due the 10th. I've dated the slides because beforehand there was an old date. So if you're downloading again the slides, yes, the deadline is the 10th, by the way. So for this reason, I already provided like the specifications of the coursework. but we're going to discuss those on Wednesday. So we're going to discuss together what that means. So that should help better in understanding the coursework. Thanks for asking. Any other question?